So welcome everyone for today's webinar about optimizing offshore wind to hydrogen production configurations. The aim of this webinar is to present the Ocean Hydrogen and Wind Tool. I am Marie Robert, Scientific Coordinator of the OFARM2 project, and together with my colleague Nicolas Michelet, who is the main developer of the tool, we will present the context of the tool development, the tool itself, some examples of how we have used the tool until now, and some services that CFEM can provide around the tool. So we are starting with the context of the tool development. And the first question is about why hydrogen and offshore wind. So there are some advantages and some barriers. Among the advantages, the important advantages, we can name the fact that it could enhance the energy sovereignty of countries with high offshore wind potential, making use of abundant remote offshore energy resources that would maybe hard to harvest otherwise. It could limit also grid congestion in onshore connections of major offshore wind hubs. So here on the right, we have a little graph that explains this, showing with the color the level of congestion or the frequency of congestion for regular wind farms, and what hydrogen could bring in a simplistic way could be to limit the congestion this way. Offshore, we are also able to produce hydrogen without drawing on the drinking water supply, and we have space to develop gigawatt-scale electrolysis facilities. Having offshore hydrogen production has also challenges, among which there is the fact that we would like to keep costs reasonable. And for that, deciding the right offshore wind farm to hydrogen coupling through a good plant layout is one of the key points. Having a proper sizing for infrastructure is also a key point, and we hope that the tool can help make the first steps in these directions. Among the challenges, there is also the management of the intermittency and the related aging and the maintenance that will come with it. There is also the fact that there are potential impacts on offshore ecosystems, and that to mitigate those impacts, we should anticipate them. And for that, again, we hope that the tool can help make the first steps. And lastly, there is also the fact that we have to prepare for the integration of this hydrogen into the market. Back in 2021, at France Energy Marine, we had those questions about the architecture that would be suited for such a coupling. And the key questions we had in mind were, would it be onshore or offshore electrolysis? Would it be on-grid or off-grid electrolysis if offshore? What should the production strategy be? Should we have a priority on electricity and do peak shaving with hydrogen production? Or should we have a priority on hydrogen? Or should we just have 100% dedicated infrastructure for hydrogen? What would be the cost of hydrogen produced offshore? What should the size of the electrolyzer be related to the size of the nominal power of the offshore wind farm? And should we transport by pipe or by ship? So to answer those questions, we decided to build a few configurations, some with onshore electrolysis, as shown on the graph, on the left part of the graph, some with offshore electrolysis, as shown on the right part of the graph. We had some variations among those configurations, with centralized or decentralized configuration for offshore production, transport by ship or by pipe, and also the possibility to distribute hydrogen offshore or to collect it from other ships offshore. The aim of those configuration was to assess them and to provide some answers for the questions on the left. So we decided to build our own tool to have a complete understanding of the hypothesis behind and some control over it. So we think that this tool can now help making some go-no-go decisions. It can help make the right choices in pre-design stages with LCOH gains that can be really significant in early choices. Sorry about that. So the tool was developed through two major projects, which were collaborative projects. The projects were named OFARM and OFARM-2. They were launched in 2021 and 2023. And OFARM stands for Offshore Production of Hydrogen Analysis and Roadmap. OFARM-2 is an advanced analysis of those production strategies. Those collaborative projects brought together some academia, some industry members, and some SMEs and other structures around some key topics, among which market analysis, assessment of hydrogen production configurations, some roadmaps for research on this topic, network integration, technology specification and sizing, and environmental integration. If you want to know more about those projects, you can look up the QR codes. I will have a quick word about some findings that we had in those projects through the use of the tool. So in the OFARM project, we really worked at farm scale, looking at what could be done for one wind farm. And what appeared is that 100% configurations are the most efficient in a cost perspective. Configuration with electrolysis capacity around 25% of the offshore wind farms were also favorable in terms of costs and certainly also in terms of flexibility. The LTOH for offshore and onshore production cases were close, and we believe that other criteria than costs will distinguish them. And exporting by pipe is more economical than by ship. So those statements, I think, are quite clear now for the industry, but back in 2023, we were happy to be able to prove that through the use of the tool. During the second project, we took a step back and made the analysis of the potential for offshore hydrogen production along various French coastlines, so in the Channel, in the Atlantic Ocean, and in the Mediterranean Sea. We distributed some hubs, and whilst ensuring the electricity generation in line with the TSO's roadmap, we showed that the French national hydrogen consumption of 900 kilotons per year could be addressed, provided that a sufficient number of offshore wind farm hubs would be developed. What I mean by this is that there is space offshore. In the national configuration that would allow to address the consumption, 50% of the hydrogen production would then be covered in the Atlantic area. We also saw through this analysis that when we have wind farms that do electricity, wind farms that do hydrogen, the most efficient is to have the electricity production close to shore and the hydrogen production further offshore. And lastly, an important thing that we looked at in this analysis was also to take advantage of the fact that the tool is at an hourly time scale. So it can provide you can have some analysis on both the seasonal and the diurnal signals. What we show here on the graph is on the x-axis, you have the months, and in the y-axis, you have the time of the day. So we see that in the Atlantic area, there is a significant diurnal signal and also a significant seasonal signal, which could be balanced quite well with the use of PV, for example. So this is the kind of analysis that can be done with the tool. And now I will give the floor to Nicolas for the presentation of the tool itself.
Thank you. Hello, everyone. So I will present you the tool itself, but right before we go into the graphical interface, we'll just give you a quick overview of how it works. So this tool is made to build some scenarios using two different elements. So we have the processes and the controllers. I will go into details of these elements after, but just for you to know, the processes are the elements of the wind farm. So we talk about the wind turbines, the substations, the cables, but also the electrolyzers, pipelines, or ships. So what we need to build our farm scenario. So the tool works with first building a scenario. So we define what elements we want in our wind farm, and then we provide some technical inputs. For example, for the wind turbines, we have the nominal power, the distance to shore. The electrolyzers, we have the location, and how we want to export our hydrogen production. So it can be through pipes or using ships. And then after we have completed the technical inputs, we need the cost inputs, so the whole expenditures of the wind farm, so capital expenditure, operational expenditure. And for that, the user can provide its own data, but we have also a default database inside the tool to help anyone to use it. So this database was built upon bibliographic review, but also some data coming from industrials. And then by combining these two main elements of the tool, after the calculation, it gives us some indicators. So we have the production, for example, the how much kilograms of H2 we have produced per year. And we have some economic indicators, such as the levelized cost of hydrogen, and some time series if we want to go deeper into the details of the calculation. To show you how it works and to demonstrate the capabilities of this tool, we have prepared for you three different cases for today. Our first two cases were built upon one question. So, is a production of hydrogen offshore more expensive than onshore? So for that, we have created two fictional tools. It does not represent any wind farm, existing wind farm, actually. So we have positioned 66 wind turbines of 15 megawatts nominal power each, 50 kilometers offshore, with an average bathymetry of 50 meters. We connect these turbines to the substation. And upon the substation, we have an electrolyzer that is designed to handle the whole production of the wind farm. So we export after that our hydrogen production through the pipes. We can see the green line on the schema and connect it to the grid at the end. So this is the first case. And the second case is an onshore production. So we have a more conventional wind farm here. With an export of the production through export cables there. And then we position our electrolyzer onshore and connect it to the grid after. And then the third case I will show you is built upon one question. Is it worthwhile to produce hydrogen to smooth out my electricity output? So on this scenario, we have built a configuration where we have a mixed production. So we position a small electrolyzer upon the substation with a nominal capacity of 250 megawatts. And then we configure to have export cables to export the rest of the electricity production. And then we prioritize the hydrogen production, meaning that if our production of electricity is lower than the capacity of the electrolyzer, then we will export only hydrogen. But if it's higher, we export hydrogen with an electrolyzer at nominal capacity, and the rest is exported through the cables. So here we have the graphical interface of this tool. As you can see, I am in a web browser, so this is a tool that will be accessible using a URL. Sorry. For now, it's running on my computer, but soon it will be deployed on the France Energy Mine server. The interface of the tool is built with 3 different tabs. We have the input tabs, so we have the visually here. Then we have the outputs tab and the documentation. We'll go into these 2 tabs after, but first we go into the inputs. So in the inputs, we have 3 panels. On the left, we have the control panel where we can create our different processes. For example, I can create a wind process and a wind turbine process. And then these elements go into the overview. So the overview will give us a visual look on our configuration to really build in with the different visual buttons, etc. In this, and then we have the third tab on the right where we have the output, the inputs. So here by default we have the general inputs. Here we can see the project name. I can change it just for you to know. And then we have several different inputs. I will not go into details for all inputs, but just for you to know, if you do not know what it means, we have small buttons on each input with tooltips that give us a small explanation of what is this input. Sorry about that. So in the overview, we build our architecture, our wind farm, by adding some processes. Here, for example, I have added a wind process, which handles the wind data, and the wind turbine process, which represent all the wind turbines. But for now, the model do not know that they are connected to each other. And this is why I need to add a controller. So I can click on this button to add a controller. I can put it in the middle of the 2. If I double click on it or on the others, of course, we can see that the inputs show me the inputs of this controller. We can see that here we have the process in and process out. We have no connections for now. To create our connections, we just need to use the button on the controller. So I click on this button and I'll press on the process I want to connect. And then I create my connection. So I have process in, so the inputs process is W1, so the wind process. And then I can connect the out process out to the wind turbine by using the button on the bottom. So now I load our first case. So I show you a complete architecture here. So here we have our first case where we have a wind farm entirely dedicated to hydrogen production, and we have our electrolyzer on offshore on the substation. So we can see here the wind data. So the wind process, I can open it and we can see that as an input, I have loaded a file where I have the time series of the wind. I have my wind turbines. So here I can see that I have 66 wind turbines with a power curve based on the NRL 15 megawatts. So 66 turbines of 15 megawatts nominal power. And then I have other elements. They are positioned with a water depth of 50 meters and 50 kilometers offshore. Then I connect my wind turbines to inter-array cables to gather the electricity from each wind turbines, so 66 inter-array cables. And then I connect them to my hydrogen production process, which represents all the installations I need to produce my hydrogen, but also to compress it to export it through the pipes or through ships if I want. We can see that my hydrogen production process is located on the substation here, and it has a nominal capacity of about 900 megawatts for here. But then I also need to define here, since I'm offshore, I need a desalination installation. So I define how much liters of fresh water I need per kilograms of H2, and then the capex and the opex of this installation, and also the compression installation I need. So I will export my hydrogen through pipes with a pressure of 80 bars, for example. And then, since I've positioned my process upon a substation, I need to add this substation, or in this case, this platform. So I add a process substation to add some capex for the offshore platform. And then I connect it to the pipe, which exports my production to the onshore facility. And this onshore process, I just define that I have a pipe of 10 kilometers that links my production to the grid onshore. And then I finish my architecture there. I can run it, so you can see that it is actually running. So we have a progress bar here, and then we have a message that says that the calculation is complete. And then we can go to the output tab. So in the output tab, we have one tab per different process, so we can have a detailed information on each processes, and an economic tab, which gives us different outputs, such as the capex and opex of each element, also the total. We have the pie chart here, giving us the repartition. And then we have other more general elements. Here we have the annual electricity production. You can see about 3,000 gigawatt-hour per year. How much we have generated of hydrogen, so the annual hydrogen production, about 56,000 tons per year, and how much it costs. So we have a levelized cost of hydrogen of 10.6 euros per kilogram for this case. And then we can go into the different elements if we want to see what happens during the calculation. For each element, processes actually, we have different outputs. For now, we have the hydrogen turbines process. We can see the time series here. This is a monthly averaged time series. So any process have a monthly average plots, because we have a 20 years simulation here, so it's way easier to look into it. So we have our time series of production. We have the capacity factor on this process. We can see an average value of 35% during the whole simulation. And then we can see, for example, the production distribution telling us that we produce the maximum in January and December on this area. We have these kind of plots for every process. I will not go into all of them. We do not have time. But instead, I can show you the second case with an onshore production. So I just load it here. Okay, so we have our architecture here. We still find our wind turbine, inter-array cables, and then we have the difference with the other here. We link the inter-array cables to an electrical substation. which is linked to an export cable process. And then we link this to the hydrogen production, which, as it is mentioned here, is positioned onshore. And then we connect it to the last process, the onshore process, where we have our 10 kilometers pipe exporting the production to the grid. I have already run it, so I go into the outputs, and we can see here our production. We see that the annual hydrogen production is quite the same, but we have a levelized cost of hydrogen a little bit cheaper than the previous one. We have 10.4 instead of 10.6 euros per kilogram. And then we can go, for example, into the hydrogen production. You can see the time series of production here if we want. Then I will just show you the last one, which is a much more complex architecture, but to show you an innovative functionality of this tool, which allow to prioritize or not the production between two different lines. So here we have our architecture. We can see still our wind data, wind turbines, inter-array cables. And here we can see that we have two lines. We divide the production between two lines. Here on the left, we have an electrical substation, an export cable, and an onshore process that collects electricity. And on the other side, I have an hydrogen production process, a substation, which is the platform actually here, and we have an export pipe connected to a last onshore process that collects hydrogen, this one. And then in the middle, we have this controller. As we can see, this controller is connected to the inter-array cable here, which is the process in, and as process out, we have the substation on the left. So here, the first one connected, and the hydrogen production on the right. So the second one connected. And then we can define how we want to split the production, so the electricity production here, between our two processes, and then between our two production lines. So we define that we want to prioritize one of the elements. So here we have defined that the first priority goes into the second connection, so the HP1 process, so into the hydrogen production element. So we prioritize our hydrogen production. And then we put priority 2 on the substation side to tell the model that when our electrolyzer reaches its full capacity, we send the rest to the electricity export. And then if I show you some in outputs, for here we can see that our annual electricity production is quite the same because it's the production of the wind turbines here. And at the end, we have a levelized cost of electricity of about 130 euros per megawatt hour. And in levelized cost of hydrogen, we are at 10.4, quite similar to the others. And an annual production, which is lower because we have a lower electrolyzer here. If I switch to the onshore tab here, I can show you. So we have the first onshore process that collects electricity. So we can see the time series of the electricity collected here. You can see that sometimes we have nothing, almost nothing. And then I can switch to the other onshore process and look at how much hydrogen I collect on this process. You can see the time series here. So this is a rapid overview on the functionalities of the tool. I cannot show you all the functionalities. I will need an hour, but we have included in the tool a documentation that can be accessed using the third tab on the documentation, where we have a definition and a description of all the processes, so wind turbines, hydrogen production, etc. Definition on all the controllers and the possibility with the controllers. So we can see we have the default controllers and we have the split, as I just show you here. We have the getting started to help users to start filling the inputs of each element. And then the first and all the case I just show you here are there on the tutorial case. So we have the simple case tutorial where we have the 100% production of hydrogen. So the first and second case, we can see that we have the documentation to show you how to create these cases. So this is an overview of the tool, and I will go, I give you back the floor, Marie, to continue on the presentation.
Thank you very much, Nicolas, for the presentation of the tool. Now we will go through some examples of how we have used the tool until now. And the first example is about assessment of different configuration for a given wind farm or a hub. So, and this assessment can be done on different kinds of criteria, can be done on the annual energy production. Energy can be electricity or hydrogen, can be done on cost, on LCOH or LCOE, can be done on production profile, as Nicolas showed. And here is an example of a plot that we had through the OFARM project. It's for a wind farm in the Atlantic economical zone of France. And here it's for a bottom fixed wind farm, and we can see the CapEx criteria, and we can see how it is split for different cases among. We can see how the CapEx is split among the different elements for different cases. So we have cases where the electrolysis happens offshore, cases where it happens onshore. We have decentralized and centralized cases. We have export by pipe and by ship. So that gives the first example. Then we also mentioned that we have the opportunity to derive hourly production profiles at different scales again, and with the possibility to represent mixed configurations involving electricity and hydrogen production. And for those two, you will be able to get the hourly production profiles. Another way we used the tool was to feed some realistic technological or environmental studies. So, for example, for technological studies, it could be studies about the long-term fatigue of electrolyzer, and you want to have a realistic profile for hourly production rates. So it could the tool could be used to define what will be the power input for the electrolyzer, or for example, tests that would run over several months in a lab. It will not provide second things at time step that would be a second, but you will have realistic things at an hourly time step. For the environmental studies, it can be used to see what is the water consumption, what is the produced water discharge. By produced water, we mean the water that would come out of a production plant that would be offshore. That would be a mix of salt, warm water, and chemicals that could be used for the treatment of the different processes. And we could also have the hydrogen production profiles, and there we can couple it either with some numerical modeling of the plume that would come out of the wind farm, or to experiments where we would impose things on species to see how they react to plausible water discharge. So this is another example. Now, if you want to talk about the practical access to the tool, it will be delivered as a software as a service. So as Nicolas mentioned, you will just have to connect to a platform and then to use it, and the calculations will be performed at France Énergie Marine. As you saw, the calculation is not very heavy, but so it's meant to be very easy to use for any level of knowledge of computers. The cost of the license will depend on your status. So if you are interested in this, we invite you to get in touch with us to define this. There will be support, which could be either for case design, launch, analysis, or maybe bug treatment. And the software will be available in September 2026. So once the license has been purchased, you can use it independently, but we will be keen to hear about the different ways in which it will be used. And in addition, FEM can also support you in various ways with the use of the tool through a range of services. So now we will take a look at those. So an example of things that France Énergie Marine could help you do would be some optimization study of a wind farm configuration. So we would build on the expertise that has been developed over research cases, and with the ability to launch many cases with small variations of inputs, the ability to analyze the results of an important number of cases, and the criteria for optimization may include annual energy production, LCOH, storage size, or some other things to be defined together. Who could benefit from those kind of studies? Maybe offshore wind farm developers, maybe potential power purchase agreement clients, maybe decision makers on tenders, and this is not exclusive. What we can also help you do would be assessment of the offshore hydrogen production potential at the scale of a sea basin. And there we can help with the definition of hypothesis and scenario with the client, and we know that it's a very important step. And then we can make good use of the modularity of the tool to represent hubs. And then we can derive some production profiles at different time scales, including hourly time series. And who could benefit from this, we think? It could be regions, it could be states, it could be electricity and gas network operators, it could be, again, decision makers on tenders, it could be consultancies. Another thing that we have been doing is sensitivity studies. And the aim can be twofold. It can be either assessing the impact of uncertainties, and because the quality of the result will depend a lot on the quality of the inputs that we put through the tool. And for some, there are some remaining uncertainties, and it's important to know what is the impact on the final results. So it's a first way of doing a sensitivity study. And then there is another way of thinking about it, is to identify on which elements of the production line it is most important to dedicate research effort. Here on the left, sorry, what you can see is a small study that we had done to see what was the impact of the capex of turbines, what is the impact of the cost of the offshore substation, what is the impact of the performance of the electrolyzer, what is the impact of the actualization rate, and what is the impact of the cost of export cable. And so with realistic variations, we saw what would be the impact on LCOH. So that can also help orientate the research effort on the right pathways. And since for those reasons, we believe that regions, states, hydrogen project developers, consultancies, and research program managers could benefit from those kind of studies. And the last one is about coupling with other modeling. As we saw in previous slides, we can use the outputs of the OFARM tool to feed either experimental or numerical studies. And it can be done by hand, but it can also be done more in depth. So we are fully open to this. And here we think that this could be beneficial for people who develop hydrogen technologies, such as electrolysis, compression, and who want to have some realistic input profiles, laboratories, non-governmental organizations who would want to have some to run some environmental impact studies, or TSOs. Then we are also open to evolutions of the tool according to your needs, and that would require obviously maybe more work than just a study, but it's something that is really open. So it could be the development of specific modules to add other sources of energy, other energy hydrogen derivatives. It could be a connection to a tool that you develop in-house in your structure, and it could also address maybe new questions that we have not pre-identified. We are reaching the conclusion, so just a few points to sum up the webinar. The tool will be available in September 2026 as a software as a service. So you will get access to what is the result of 5 years of tool development and usage for research topics. We hope that it's an intuitive tool, and we think that it's an intuitive tool with rapid onboarding and optimized execution times, and we think it's a strong point. It's applicable anywhere in the world as long as you have a time series for the wind. And the support is available at every stage of your project if it's needed. So that's it for us. And I think that we have a few questions in the chat. We can now get through them if you want. Thank you, everyone. And we had a last slide. Yes, we are available now to answer your questions together with our colleague Lenaïg Melaza, who is the project manager of the OFARM-2 project. And if you need further information, you can write us at commercial@franceenergiemarine.org. We take a close look at things that come in this mailbox.
Okay, so we had already several questions in the chat. So if you have other questions in the meantime, please do not hesitate to put them. We will maybe not be able to answer all of them at the time, but we can answer them later on. So I will just go step by step. So there was a question from Gonina Crozier regarding the simulation of water consumption and land surface required to produce onshore. So Nicolas, you can maybe answer what is taken into account in the tool.
Water consumption?
If water consumption was modeled. And this land surface was also an output of the tool
The land surface.
for onshore applications.
Yeah. So now the land surface is not an output, but we have included the simulation of water consumption. As you see, we have an input to define how much liters of fresh water is needed to generate kilograms of hydrogen, and this is an output of the tool that we have used in our environmental studies is the water consumption, so the time series during the 20 years. So it can be used to do other studies. Yeah.
Okay, thank you. After that, we had a question from Alice Shish regarding the pipes, the cable and the pipe. Is the tool able to determine the optimized dimensions of the cable and the pipes, or are these parameters always an input? So, Marie, you can maybe answer that.
Yes, so the short answer is no. The tool does not optimize the dimension of the cables and the pipe. It's an input that the user should specify. The maybe longer answer is that the tool can give you hints to choose the right size, because as Nicolas has showed, you can see in each process, you can have the graphs and you see what comes through the pipe or through the cable. So if you run the tool the first time, it may help you to choose the right size, but it will not tell what is the techno-economical right sizing. Maybe you can undersize a little bit and it's more beneficial. The tool will not be able to determine that. But if you undersize, you will see the consequences.
Mm-hmm.
And it is typically the type of further studies that can be developed if needed, because we could integrate that in the tool later on. Also, this feature is not integrated yet. After that, we had a question from Dan Gerdink. Is it possible to take into account power market prices and bidirectional HVDC connection that buy power onshore in time of low wind in order to produce H2 offshore and increase the capacity factor of the offshore hydrogen plant? So maybe I can answer that. Not yet. The tool does not directly make the link with the market, but it's clearly something that we have in mind for the future, and that's a further development that we would like to develop within the other projects. So we really have that in mind. For the time being, it has only been developed from a design perspective, not making the connection with the market, but it's something that would be really useful and needed for acceptability of hydrogen, and really see how have the economic model sustaining hydrogen production at sea. After that, we had a question from Christophe Brice. Do we have to enter the capex of all components, or does the software propose some values extracted from an internal database? So, Nicolas,
yes. So by default, we have a default database, a tool that it can extract the capex of the different elements. So this database, as I mentioned, was built on bibliographic review, but also some data coming from industrials. And then when you change the inputs, for example, I can take the wind turbines. If you change from a bottom fixed wind turbine to a floating wind turbine, you will see that in the tool, the capex automatically updates to fit with the floating wind turbines capex. So yeah, we have the default database, and of course, it can be override if you want. It's completely open to you.
Yeah, the default database is planned if there is no data, but every line can be modified with capex. If you have more specific data that are more tailored suited to your design, you can change the values. The default database is just there if you don't have the values. That's flexible.
By the way, I run the different cases with the default database.
I can maybe answer the question about the electrolyzer ramp up on ramp down. So the question was about, were you able to simulate electrolyzer flexibility, ramp up, ramp down in the tool? And the answer is, for now, it's not active, but as previously mentioned for the link to the market, it is something that we already have in mind. So it's among the interesting next developments. One thing that came across our mind when we examined this is that for PEM electrolyzer, for example, the ramp up time is quite short compared to 1 hour. So sometimes, so we would have to see how we integrate it in at early time steps, but we believe it would be interesting. Thank you for the question and the confirmation that it could be interesting for other people than us.
After that, sorry for the one that put new question in the chat. I will go in the order of the first question. We had a question from Maximilien Lemaine, wondering if the LCOE-H figure given is the LCOE-H BIS delivered at the end of the onshore pipeline or at the electrolyzer outlet. So yeah, really the question is, where is the cost stops of the LCOE-H? And what about the impact of the pipeline length on CapEx, OpEx, LCOE-H BIS?
Yeah, so the LCOE-H and LCOE actually are calculated at the end of this simulation line. So we are at the connection with the onshore grid. So this is why on the onshore process we add a small capex for the onshore pipe. So we can account for the connection inside the system.
We could say that it's a broad definition of LCOE and LCOE-H. It's not just at the back of the electrolyzer when it's offshore. And it's an important. Thank you for the question, because it's an important thing.
After that, we had a question regarding degradation. How did you model? How do you model electrolyzer degradation, and does the platform support managing multiple technologies simultaneously, such as alkaline and PEM electrolyzer? So I can give first hint of answer, and you can complete, Nicolas. For the time being, the tool has been developed on PEM electrolysis because that's the technology we have used in the project. And the electrolyzer degradation is taken into account with a decrease of the efficiency of the electrolyzer along time. And depending on the duration of the simulation, we also plan a replacement of some components of the electrolyzer, so that's included in the documentation.
Yes, exactly. With time, the electrolyzer inside the simulation lose in efficiency, and once we have crossed a certain threshold, we consider that we change the stack of the electrolyzer, and then the tool include this new stack inside the capital expenditure of the whole project. So, for example, for the case I showed you, in 20 years, we have 3 changes of the stack, if I remember well, which were accounted inside the whole expenditure of the wind farms.
We have also a question about hybrid configurations, and the question is, how do you allocate the cost in a hybrid connection when the electricity is shared between the electrolyzer and an HVDC line? Do you add capex and opex of wind to both LCOE and LCOE-H, or split them? And here the short answer is that we split them. It will be done according to the size of the electricity substation and the hydrogen substation. So if they are properly sized, it works well. If they are oversized, maybe it will be bad for the energy vector with a substation that is oversized.
And maybe we have time for the last question. Do you envisage to make the prioritization variable between electricity generation or hydrogen production an endogenous variable? For example, in case your future incorporation of market price for H2 and electricity wholesale market enables arbitrage between hydrogen and electricity. Tough question.
Well, this is good because we have questions of things that we want to include in the tool. So yeah, for now, we do not have a variation of the prioritization, sorry. We have two different strategies, so we can prioritize, but we can also split with a percentage if we want. But yeah, this is one thing that we would like to do in future versions when we connect the market, have a third strategy, maybe based on the electricity or hydrogen cost of the market. That would be a very great functionality.
I don't know if there is any other question. I think we have managed to answer all of them. And maybe there is last one in the Q&A.
No, I think it's okay.
There was a question from François Squet. Still, it's related to the type of software. Donc, saying that the software as a service will be a success for sure. Still, a MVP or a definitive SaaS software. I do not understand the question.
Could you explain a little bit more what is an MVP? Maybe I don't have the vocabulary, but
yeah,
maybe we will come back. We will think about it and come back to you personally, maybe. Minimum viable product. Okay, thank you.
Sorry, this one we will keep it for later. We will answer it by email. Okay. 1 minute before the deadline of the webinar and no more questions, so we really managed the time quite well, I think.
Thank you everyone for your participation.
Yeah, thank you everyone.
The presenter question. Thank you for the organization on Mathilde Roulin's side.
And the webinar, the slides and the recording will be available on a YouTube page soon, and it will be shared in the project in the website of FEM also. So you will be able to review the slides. And if in the meantime you have any question regarding the tool or ideas, we are all available around the table to hear your thoughts. So do not hesitate to get in touch with us. You will have the email in the slides.
Thank you very much, everyone.
Bye.